Welcome. Here we are again. Another beautiful afternoon where we have to talk about organic chemistry. We're getting close to the end. Only a few more lectures here. Today is day 24. Any point you have questions, feel free to unmute yourself or send me a message. And if you're watching the recording, obviously send me a message anytime. So we just barely got into chapter 22 here on Monday and started talking about the formation and property of enolates. So the first thing I want to talk about here is why would anyone want to form an enolate? And the reason is because it's a good nucleophile. And that allows us to make new carbon-carbon bonds. And that's kind of one of the main things that organic chemists want to do, is to build up the complexity of some structure and make some new compound with some novel, interesting, or potentially useful properties. So the idea here is, if I have a carbonyl compound, maybe an aldehyde for simplicity's sake, if there's even a single proton here on the alpha carbon, so there could be maybe another R group, if the right base is used, and we're going to talk about some options for bases today, that proton can be removed. The major resonance contributor that results will have a negative charge on oxygen there. That's a good nucleophile. Last time we talked about how the most likely site for the nucleophilic attack is here, and we can get that to attack an electrophile. So what's interesting, and we're going to see more examples of this as we go through today, is the possibility of using a carbonyl as the electrophile, right? We know carbonyl carbons have resonance, induction, creating a lot of partial positive here. We know that this flat around this carbon, there's not too much steric hindrance usually. So this oxygen can swing these electrons in and attack from the alpha carbon the carbonyl carbon. And that makes a new bond between these two carbons. And, I can have a fairly large chunk here, a fairly large structure here, and I can get them to connect and make a much larger structure with control over the position of the atoms. So we need a base to remove the alpha proton. So we're going to talk about that. And in this first step, where the enolate's formed, depending on how strong the base is and how unstable it is, that process, that first step, it may end up being in equilibrium, or it may be extremely product favored. So sometimes you might want the base to react with every unit of the carbonyl here to make every one of those units into an enolate. So maybe you want to be 100% product favored. You'd need a strong base. And it's something that when it picks up that proton, its conjugate acid is relatively stable compared to the acidity of the alpha proton. So what method do we have to quantify acidity, quantify strengths of acids and bases? We use pKa. So let's take a look at some of these pKa values. So here's a couple compounds. They each have alpha carbons and alpha hydrogens. And if the base were to remove one of these protons, it would produce an enolate, which could act as a nucleophile. And if we look at the pKa values for these protons, what we see is they're usually somewhere between 15 and 20. So that's similar to the pKa of water. and also similar to the pKa of alcohols. Not surprisingly, because once this proton's removed and the electrons swing in, they'll mostly swing up to the oxygen, right? This is the major contributor. And a negative charge on an oxygen, even when it's spread out through resonance and also shared over a carbon, the carbon doesn't stabilize it well, so the vast majority of it is on the oxygen, and that's not that different from the negative charge we'd get on an oxygen when water loses a proton or when an alcohol loses a proton. So their pKa's are similar because their conjugate bases are very similar in their ability to stabilize a negative charge. A couple more examples here. So we can see here my compound's a little smaller, so the pKa is a little lower, and that's because the negative charge is a little bit more stable. Why would this negative charge be more stable than this one here or this one here? And they're stabilized by resonance in each case, shared between an oxygen and a carbon in each case. So the main difference here is going to be solvation, because there's no major R groups here. It's going to be relatively easy for solvent molecules to surround the areas of negative charge and form some nice attractions there. So the acid's a little bit more able to donate a proton when the conjugate base is slightly more stable. So, as we said, that has some impact on the pKa, but the pKa value is still going to usually be between 15 and 20. So we can start to imagine some bases and how those bases might affect the equilibrium in the removal of the alpha proton and formation of the enolate. So just take a look at ethoxide. It's a common base that we used a lot both this semester and last semester, mostly in removing protons to do elimination reactions. It's also a decent nucleophile. So you could also imagine, let's just explore this idea real quick, it attacking the carbonyl carbon and pushing electrons up here. So if that were to occur, what would we get? We would get negative here. We would have the OET there. So that doesn't look terrible, and we got a negative on an oxygen here. There's no resonance to stabilize it. So in that regard, it's less likely to form versus what we're seeing here on the slide, which is the removal of the alpha proton to form a resonance stabilized negative. So stabilizing the negative of an oxygen and a carbon, slightly more stable than on an oxygen. The other disadvantage that this structure here has is sterics. So there's a methyl group here and an OET. It's going to create a little sterics. We don't really have that when we just pick off the alpha proton and form a much smaller structure. And then thirdly, entropy. Right? If we combine these two structures together to make one thing, there's going to be less entropy and variety associated with that thing's position and movement than there would be if it picks off a proton to produce 2 moles of products that can independently move around and has a lot more entropy. So the entropy disadvantage, the sterics disadvantage, and the negative charge on the oxygen not being well solvated because of sterics and not being stabilized by resonance are the main reasons why this won't attack the carbonyl as often. And if it does, the oxygen will usually swing back electrons and push it back out because it's really the only leaving group here. The R group or proton that's connected here wouldn't leave. So even though it's not unreasonable to imagine this as a nucleophile attacking the carbonyl carbon, it's probably more likely to pick off a proton to produce the enolate. And if we look at the pKa values on either side of this equilibrium, we know the equilibrium will favor the side with the higher pKa because that's a more stable acid compared to the other acid. And we can verify that conceptually by recognizing that this OET is relatively small, be pretty well solvated, and so it's slightly more stable than the enolate. And so whichever side has a more stable base will also have the more stable acid and the higher pKa. So that means this side is slightly favored in equilibrium. So we might draw that arrow a little longer than the other one. But the pKa's are very close. It's about 1 unit difference. And we know every pKa unit difference, 1 pKa unit, equals 10 times more on that side of the equilibrium. So if this pKa is about a unit higher than the other one, which is not even quite a full unit, it means you're going to have about 10 times more of the substances in this form versus for every one instance where you have the substances in this other form. So since the equilibrium here favors the reactants, does that mean we can't use this reaction, making an enolate that isn't really favored over the base? Is that still practical? Yeah, because even if I form a little bit of it, if I can get that to react with an electrophile to produce some products, if that step is very product favored, then by Le Chatelier's principle, it should slowly take the amount of this out of solution and convert it into something else, and then this reaction will have to shift back toward the product side to reform its equilibrium. So even when the first step of this process isn't product favored because the enolate's not quite as stable as the base, I can still shift it toward the product side if I can convert that enolate into something else in an extremely product favored way. So this is one strategy to use a base that's similar in strength to the enolate, or similar in stability to the enolate, so you'll form an equilibrium. And we'll discuss why you would ever want to do that. So in this case, that's actually what we're trying to do. We want to have both the base and the enolate in equilibrium at the same time. We're not so interested in having the base around as much as we're interested in having both sides of the equilibrium present, because that provides us, when only some of these carbonyl compounds are converted into the enolate, it provides us with a situation where the enolate that has formed, some of the molecules have formed into this, can attack the remaining molecules that remain in the reactants, the form of the reactants. So that's the idea here. This is one strategy. In this strategy, we want to create an equilibrium so that both of these structures will exist simultaneously at equilibrium, and they can then collide with one another. And so that would look like this. You'd have your enolate, which you could draw in either resonance contributor. Oops. Yeah, it doesn't look good. I'll draw it here. Either resonance contributor, and then that would generally attack from the carbon. So that would be making up part of this equilibrium, and the other part of the equilibrium would be acting as an electrophile. So we could imagine the enolate attacking. We could also show, if we looked at the other contributor, we can imagine those electrons swinging in and then that attacking. Either way, it's this alpha carbon that's going to attack the carbonyl. So this structure reforms the CO double bond, and then the alpha carbon attacks the carbonyl carbon. So it makes a new carbon-carbon bond, and when it attacks there, these electrons are going to swing up to the oxygen there. So as we're saying, both of these are formed in equilibrium, and we can have one attack the other, or it will naturally attack the other when they happen to naturally collide. The negative side of one and the partial positive of the other will attract and invite that collision to occur. And then this could pick off a proton here and regenerate the base, which can continue reacting, and that would produce something called an aldol. We're going to talk about the Aldol reaction. Aldol is a combination of two words, aldehyde and alcohol. And that's because, that's that proton. That's because you're forming an aldehyde and an alcohol on the same compound. So that's the idea there. We want to set up an equilibrium so we have the nucleophile and electrophile in equilibrium together, and then they can collide and produce a product. Sometimes you don't want that to occur. So if you wanted to convert all of the alpha protons and remove all of them and convert all of the carbonyl compound into an enolate so that you can add some other electrophile. And so the strategy on the last slide would only be useful if the enolate we produce, if we want that to specifically attack the carbonyl that the enolate was formed from. But if we wanted to attack some other carbonyl or some other electrophile, we might want to convert all the molecules into an enolate in one step, where we add a stronger base, and then in a second step, add an electrophile that can attack. So that's when that is synthetically desirable. If we want all of that to convert to an enolate because we're going to add a totally different electrophile that we want that to attack. And the H- is very unstable. So if we're adding like sodium hydride, that would pick off the proton in a way that dramatically favors the product. The hydride picking up proton would produce hydrogen gas. And so the pKa of this is somewhere around 15 to 20. The pKa of hydrogen gas, I think, is closer to 35 or something like that. I know it's much greater. I'll just say it's around 30 probably. But it's at least 10 units more. So that means this isn't much of an equilibrium. I'm getting almost a billion or a trillion times more products than I have reactants. So that effectively converts that all into the enolate, and that doesn't produce much of an equilibrium. So if all the reactants are converted into the enolate in one step, then you can add the electrophile later and have the enolate attack it. So that's the other strategy. So there's really kind of two strategies here. Form an equilibrium where the two components of the equilibrium attack one another, or try to get all of the reactant to be converted into an enolate and then later add another electrophile for it to attack. Another strong base that has a very high pKa and will pick off an alpha proton to form an enolate in a way that is not really reversible because the reverse reaction is really insignificant due to the large pKa difference. So here the pKa difference is on the order of 20 pKa units, so I'm going to have 10 to the 20th products for every one reactant. So that's really effectively 100% for all intents and purposes. And again, the purpose of this would be to convert all of this substrate into an enolate nucleophile, and then later you would add some electrophile for it to attack. So why is the reaction effectively irreversible? It's not technically irreversible. This could definitely pick a proton back up and go back. And you could easily imagine that mechanism, and once in a while that collision will occur and it will go back. But because the stability of this negative charge, which is mainly existing on an oxygen and stabilized through resonance, is way more stable than the negative charge on the smaller nitrogen that's not stabilized by resonance and has these bulky groups around it to prevent effective solvation, making it even less stable. That means that it's really going to favor the more stable side by a huge margin. And so we could say the difference in the pKa units is so great that it really only effectively favors the side that is much more stable with the higher pKa. So there's really two reasons here why this compound is used in the form where it has these two bulky isopropyl groups. One is it makes the base even less stable and more reactive and more likely to shift to the product side because it's not well solvated. Right? So wherever the solvent is, it's going to be hard for it to come in here with some partial positive and attract to this negative and stabilize it. That makes it even more unstable and more likely to react, and it makes the equilibrium even more product favored. The second reason is because it will give us some control over regiochemical outcome or regioselectivity. So what we mean there is if I have two different alpha carbons that aren't equivalent, maybe one has more R groups and the other one has protons. In a situation like this, you could form two different enolates. If the base picks off this proton, I form an enolate on this side. If the base picks off this proton, then the electrons here would stay behind, and I would form an enolate on the other side. That will control which alpha carbon is nucleophilic and which alpha carbon attacks and the electrophile to form a new bond. And so that's the nice thing about this reagent. It's bulky enough where if it were to come in and attack here, the bulkiness of this and the bulkiness of the R groups would create a lot of steric hindrance during the transition state. So that would be an unlikely transition state for it to go through. And so when I have a bulky base that's especially strong, I can expect the majority of the product to result from it picking off a proton from the less sterically hindered side to avoid all that steric hindrance during the transition state. And that's going to form an enolate in a predictable way. So if I specifically want that enolate rather than the other one, and I want that one's negative charge to attack an electrophile, that's when I would use that bulky base. So the regioselectivity or the region or alpha carbon where the reaction occurs depends in part on how bulky the base is. Alternatively, let's imagine here if we used hydride. So let's say we've got this compound still. We've got these big R groups here. If we use a hydride, in that case, I would expect it to pick off this proton. Specifically because the enolate that results has a more substituted and more stable carbon-carbon double bond in its major contributor. So there's not really, steric's not an issue here because it's a super tiny, negatively charged, very strong base. Really, it will pick off whatever proton it collides with, but it will more often go through a transition state to pick off the proton that starts to form a pi bond between substitutes, between carbons that are more substituted, because that's a lower energy transition state. So again, we can control which carbon of the two alpha carbons a proton is removed from using sterics if there's a difference in a steric difference between the two alpha carbons, because one's more sterically hindered than the other. You should know that if a alpha carbon is alpha to two different carbonyls, its pK is going to be even lower. And that's because whatever base you use, if you pick off that proton, you'll produce a compound that has extra resonance stabilization. So it's much easier to do that, right? So here's one resonance contributor. The electrons can swing up to this oxygen, stabilizing the negative on an oxygen, or they can swing up to this oxygen. I mean, technically they're not swinging around anywhere. What you get is the average or resonance hybrid, but the resonance hybrid is going to be a lot more stable if the negative is instantly spread out between the carbon and primarily on two different oxygens. That's going to be only a fraction of a negative on each of those atoms, so it's going to be a lot more stable. Right? So the more atoms the negative can be spread out over, the more stable it will be. And when the conjugate base, which would be the resonance hybrid of these three, is formed, because it's so stable, that means that the acid is stronger and will more readily donate a proton. So that means for this particular acid, its pK is low enough that even an ethoxide, which we said once it picks up a proton has a pK of about 16, that's enough to pretty much effectively convert all of the compound into the enolate. Because when we look at the pKa difference between 9 and 16, it's about 7 pKa units, so it's going to be 10 to the 7th products for every one reactant. That's effectively 10 million times more products and reactants is effectively not much of an equilibrium. So we can effectively call that an irreversible process. So you want to be aware of how the extra resonance for the enolate can stabilize it so much that it can be, you can convert all of your reactant into the enolate depending on the base you use. But ultimately, if you know the pKa values, that would be the best way to judge the degree to which this equilibrium shifts and favors one side versus the other. So what are some electrophiles that we can have enolates react with? One electrophile is a halogen. Right? We know generally that a nucleophile can attack a halogen, even though it's nonpolar. It can have a temporary dipole. If the electrons just happen to randomly shift to one side, that would create a partial positive here to attract the negative of the nucleophile. The main thing about a halogen molecule that makes it a good electrophile is its leaving group, right? So if the nucleophile attacks and it pushes out a Br minus, we know Cl minus, Br minus, I minus, those are all really stable leaving groups, and so that occurs pretty readily. It occurs so readily that the nucleophile doesn't even have to be negatively charged. It could be neutral. So one way to do this reaction, which ultimately is involving conversion of an alpha proton into a halide, so we're doing a substitution reaction, removing a proton, replacing it with a halogen, is to first use the acid necessary to catalyze the ketone-enol tautomerization reaction that produces an enol. So we got a ketone, enol. We know these are in equilibrium, and we know the equilibrium favors the ketone for almost every carbonyl compound. We saw a couple examples on Monday where this equilibrium favors the enol side, but that's quite rare because normally the CO double bond is a lot more stable than a CC double bond. So even though this equilibrium pretty dramatically favors the reactant side, if a small amount of this exists in equilibrium, which it will, and there's no way to stop it, that is nucleophilic enough that these electrons can swing in, and the pi electrons here can attack this and push out a Br minus, which is a really very stable product. And then usually you'd have a solvent like water to pick up that proton and give you this as your main product of interest. When the water picks off that proton, it regenerates H3O+, which then goes on to catalyze this tautomerization reaction that we talked about last time. So that's one way to replace an alpha proton with a halogen. You can do that under acidic conditions with H3O+ and the halogen molecule through this mechanism. So if we were to think about that example, so this H plus just represents H3O plus, so it's the same reaction we just looked at. If you have a carbonyl compound that has, like a ketone that has two different alpha carbons that are not equivalent because obviously one side has a methyl group, the other side doesn't, then you have to consider the possibility of the reaction occurring at either side. So what will be happening here is the acid catalyst is going to convert this into two different enols. The acid would first protonate the oxygen. Once it's protonated, it really does attract these electrons up quite strongly. And then a water can pick off either this proton, swing all these electrons down as those move up to the oxygen, or it could pick off one of the other protons and swing those electrons in as the pi electrons move up to the oxygen. So if it comes in and picks off this proton, I would get this enol here. If it collides over here and picks off this proton, I would get this enol here. Oops, should be OH. So if we're looking at those two pathways, we'll call this A and B, and we're interested in the kinetics of that process, this ketone starts at a certain energy, BH3O plus starts at a certain energy, so the reactant energy would be reflective of those, how stable those compounds are. Once the oxygen gets protonated, it's going to be probably a pretty fast step, the proton transfer to protonate the oxygen. And that should be a product favorite step because this oxygen can stabilize its negative through resonance, whereas the H3O plus cannot. So then when a water picks off this proton, that's where we're looking at the difference between picking off one alpha proton versus another. If we pick off the proton that gives us A, that pathway goes through, that's a slow step. That pathway goes through lower energy transition state. Because the carbon-carbon double bond is more substituted with carbon groups. It's got 3 of them. Versus if the water picks off proton and goes through pathway B, it's going to be higher in energy because the carbon-carbon double bond is less substituted with carbon groups because it's now substituted with the hydrogen. So that allows us to explain why we get the difference between which product is the major product and which product is the minor product in this reaction. Because if the water picks off this proton to create this enol, and when the electrons swing back in, it would attack from this carbon, it would attack the Br2, and that's why the Br ends up on that carbon. Then obviously the oxygen would be deprotonated with the water, and I would get the CO double bond to reform. I can't form the minor product unless it goes through the slow step through a higher energy pathway, and that's not going to happen nearly as often, which is why the product that results from that is minor. And so if this oxygen swings its electrons in and pushes this pi electron to add a bromine, and it adds to the other side here, it's not going to happen as often. Not because it can't readily attack the bromine, but because it doesn't form into an enolate as often, because it's just not as stable an enolate as the other one when its pi bond isn't as substituted with carbon groups. However, we still would probably get significant amounts of both because the energy difference here is not probably as big as I've made it out to be. And so getting a mixture of products is not really ideal. So in all, one other thing that you can do after that reaction, right? So we said this oxygen would pick up this proton, that makes the alpha protons much more acidic than they normally would be. So even a base like water, Puridine's not present yet, would be added till later. As we said, could pick off this proton, form the most substituted enol there. That would swing these electrons up here. So we would then expect that to attack bromine. These electrons would swing back down. And then a water, deprotonate that. So that would form an intermediate, which is basically the product we saw in the last slide, the major product. And then if we want to form a pi bond here, which is nicely conjugated with the pi bond, the CO double bond pi bond, that conjugation creates pure overlap between all four of those atoms, creating some nice molecular orbitals to stabilize those pi electrons pretty well. The pyridine would be present to pick off this proton. So once this proton, whichever of these protons is anti-periplanar to the leaving group, the pyridine would pick that off and kick out the leaving group. So the idea here is replacing a proton with a leaving group so that we can set up an E2 elimination reaction and form a pi bond. And we'll see later in the semester how these compounds are especially useful in syntheses. We don't need pyridine necessarily. We could also use a different base to pick off that proton. A very sterically hindered base, though, might actually pick off this proton because it's on the methyl group out here and it's not as much sterics, and if it picks up that proton to push out the bromine, you might get a different regiochemical outcome. That would look like that. Right, so we're applying the concepts we've been talking about since last semester here to try to understand why we get these products and control the products that we form. So an alternative way to replace a hydrogen with a leaving group, a halogen specifically, would be to use basic conditions. So in this particular example, I've got methyl groups here, so there is no proton at this carbon. If there's no proton here, then the base can't pick anything off. There's not going to be any reaction occurring. So anytime I have a base reacting with a carbonyl compound, I want to check both alpha carbons to see which one the base might be more able to pick a proton off of. And if there's no proton there, then obviously I'm not worried about the reaction occurring over there. I'm worried about the reaction occurring where the base picks off an alpha proton. Now this first step would probably actually be a little bit more reactant favored than it would product favored. But as we said, when the OH minus picks up a proton and produces water, the pKa of water is comparable to the pKa of most alpha protons, so this equilibrium would produce significant amounts of both substances. But then, even though the equilibrium probably favors the reactants a little bit, if a significant amount of this did form, which we should expect because the equilibrium, the pKa's are similar, so the equilibrium is not like hugely on one side. So the small amount of this that does form is now a really nice nucleophile. So we would expect that to pretty quickly start reacting with bromine, even the weak collisions that occur here, because the negative charge that stabilized through resonance over an oxygen and a carbon is not going to be nearly as stable as the negative that results on a Br minus. So that would attack, push out a Br minus as a side product, and I've effectively added a halogen to that carbon. So this question here is really important though, because it will help us recognize a key point about this reaction. Once the bromine is present, through induction, it's withdrawing electrons from this carbon. So if I were comparing the original compound versus this compound, and imagining, is OH minus going to react with this and pick off this proton, or is it going to pick off the original proton? You can start to see an issue with this reaction. Right, so in the very beginning, when I only have hydroxide in this, or there's only one alpha proton for the hydroxide to pick off, some of the molecules be converted into this. Those would pick up a bromine or produce product. But remember, we said the equilibrium does favor the reactant side, so most of the reactants would still remain in this form. And in order to convert them all into the products, they would all, at some point or another, have to have a chance to lose a proton to produce an enolate and then collide with Br2. But that takes a while because I have to get this equilibrium to then shift toward the, as this enolate reacts and produces a product, it's being consumed from the equilibrium, so that Chaly's principle suggests the equilibrium has to shift to produce more of this intermediate to reestablish equilibrium. So as that's occurring, the product is now starting to build up in concentration because I'm forming more and more of it, and it still has an alpha proton. So now the OH might start colliding here and picking off that alpha proton. And that would produce a different enolate because now there's a bromine there. And since the bromine withdraws electrons through induction, that is an added thing that stabilizes this negative charge in addition to the resonance experiences with the oxygen and the induction of the oxygen creating positive to help stabilize that negative. So that means that the product is even more likely to donate a proton than the initial reactant. And it will start reacting to form this enolate, and then that enolate will react with another bromine. And so that will produce a side product that you can't stop because the first product is more reactive than any unreacted remaining initial reactant. So what happens is a lot of the product gets converted into this other substance. So I really can't control this from happening. So the best bet I have here is to use excess of that. And so since I can't only form this product and get it to stop there because it's now more reactive than any unreacted initial substance, then I'm still waiting to form into the product. That will start reacting in the meantime and forming this product. I can't really isolate this as a result. And so if I use excess OH minus and excess Br, then I can really shift all of this equilibrium toward this final product. So this reaction will work, but it won't really effectively work to replace only one alpha proton with the halogen. You end up actually replacing all of the alpha protons with halogen, and that will happen for some of the molecules no matter what you do. So you might as well just embrace it and add excess of the reagents and get all of the reactants to convert into that product and accept the fact that that's the major product that you're going to end up with. If you don't want that, then obviously you wouldn't do this reaction. So here's another instance where that can occur. So again, we happen to have one of our alpha carbons with no protons, so we wouldn't expect any reaction there. Only the alpha protons should be removed because they are the ones that produce an enolate, right? If I try to pick up this proton, the electrons could stay behind, but then I'd have a negative on a carbon. It would be too far away. It would be stabilized by resonance. That would be really unstable. So we're not going to see that occurring really pretty much ever to any significant degree. Here I've got 3 alpha protons. So the idea is we're using excess of both of these reactants. And we're going to get successive reactions occurring where first the OH minus picks off one proton, electrons stay behind. That enolate attacks a Br2. And I put a Br on that carbon. And then we're using excess. That's going to happen again. OH is going to pick off the other proton. And then that's going to be replaced with the bromine. And that's going to pick off another proton and create another enolate. Once the bromine's already there, they're making the process more likely to occur because they're stabilizing the next negative that forms through induction. And then once that proton is removed and that enolate attacks another bromine, I would get another bromine connected there. If the group that's alpha to the CO double bond is a methyl specifically, which this one is, and only if it's a methyl, then you'll have 3 alpha protons, and if each one is picked off one at a time and replaced with the bromine through this mechanism, or an iodine, or a chlorine, now you have 3 really pretty electronegative atoms pulling a lot of electron density away from here. So what's going to happen next, and since I have excess OH minus, there's plenty still around, is the OH minus is now going to attack the carbonyl. Right, we said earlier that's not very likely. We were talking about OAT, but it's basically the same idea, OH, OAT, either way. If that attacks here and pushes electrons up, OH minus is not that strong of a nucleophile. When that occurs, and produces this intermediate, what you'd probably expect to happen is that the oxygen would swing back down and push out the OH and just go back. That could happen sometimes. But once in a while, if it attacks and the oxygen swings back down, I can see a carbon leaving group leave. Normally a carbon won't leave, but because these bromines are here withdrawing electrons, that carbon leaving group that leaves now has 3 bromines on it. So even though it's negative, a lot of that electron density is withdrawn and spread out over the bromines through induction. That really is enough to stabilize that negative. But in order for that to happen, you need to have 3 halides, not 2 or 1. That wouldn't do enough. We need 3 to pull enough electron density away from that carbon and its negative for it to actually be able to leave and form a negative. It's still pretty unstable with the negative though, so it would quickly pick off a proton and these electrons would stay here, and I would get an even more stable resonance stabilized negative and CHBr3, which is bromoform. And then the purpose of the H3O plus is just to protonate that and convert it into a carboxylic acid. So this is another way to make a carboxylic acid. This decreases the number of carbons. It only works if my carbonyl has a methyl on one side. If it has 2 different R groups, this reaction I won't be able to make a carboxylic acid. It has to be a methyl group specifically because a methyl group has 3 protons, and if all 3 are replaced with bromines, that makes a good enough leaving group that when the hydroxide attacks, it can leave. And then when it leaves, it'll pick off a proton. It won't come back in because of sterics. It'll pick off a proton. And essentially that step is irreversible because the negative is a lot more stable over 2 oxygens than on a carbon, even if there is induction to stabilize it. So that reaction actually works pretty well. Here's the mechanism all written out for you. As we said, the last step is practically reversible because this oxygen is way more stable, sharing that through resonance versus the carbon. And that reaction works with chlorine, bromine, or iodine. It's called the haloform reaction because it produces either chloroform, bromoform, or iodoform. And iodoform is a nice, easily observable yellow solid. And so for a long time, before we had NMR and IR and mass spec and all these really great techniques for determining the structure of a compound, they had to use these chemical tests. One of those chemical tests was the iodoform test. So if you suspected that your compound had a methyl group specifically, you could react it with excess NaOH and iodine in one step, and that would produce iodoform, which is a yellow solid. If you saw the appearance of that yellow solid, that would confirm you had a methyl group. Because any other group wouldn't be able to leave any other group. Like if I had an ethyl group here, the excess OH minus would still pick off these protons, and then the enolate would still attack an iodine to produce an I minus leaving group, and that would occur for every alpha proton. But it's not going to be a good leaving group unless there's an iodine at all three positions. So we don't see the yellow solid unless there's specifically a methyl group where iodine can replace every proton on that group, making it a good enough leaving group to leave and then pick up a proton from the OH that attacks to produce the iodoform. So now we can answer some questions related to that reaction. Here I have 1, 2, 3, 4 alpha protons. And if I'm using excess of these reagents, I expect the NaOH to be able to pick off every one of those 4, one at a time, producing an enolate. And then the enolate would attack a Cl2, releasing a Cl minus byproduct. And so once the proton's removed and the lone pair picks up a chlorine, I would end up getting a chlorine at each one of those positions. So initially, what I would get is a chlorine here, and chlorine here, here, and here. So what about the stereochemistry at this carbon? Well, it's not a chiral center, so it doesn't really matter how I draw it. If I draw the chlorine coming out at me and this pointing away versus the chlorine pointing away and the carbonyl coming out at me, it's the same structure, just flipped over like a pancake. So it doesn't matter how I draw it. But then, now I see, since this was a methyl group, it can leave. And I expect an OH minus to come in here, push electrons up, and when they swing back down, to push that leaving group out. So once it leaves, it will then pick off a proton. So I'm not even going to show wedges and dashes because the stereochemistry doesn't really matter since it's not a chiral center here. But once this leaves, I'll have a negative on a carbon. It will pick off this proton, but then the H2O plus will provide the proton to replace that. So this would be the major product I would expect out of that reaction, along with the chloroform byproduct that would probably just evaporate out. So that is very similar to today's first quiz question. The difference here mainly is I don't have a methyl group. So in this specific case, there's still a proton here, but now there are only 2 alpha protons on this side. So the first thing I expect to happen, since I have excess of these reagents, is for every alpha proton to be replaced one by one, going through an enolate intermediate that can pick off a Cl from a Cl2. I don't expect anything to happen over here at this site because it's not alpha. There shouldn't be any stable intermediate that could occur if any reactions occur there. So I'm going to have a chlorine here and 2 chlorines here. Every alpha proton should be replaced with a halide when I'm using excess halogen and any OH. Here though, because of this methyl group, this now is a chiral center. It's got a hydrogen, the carbonyl, and then as I go around the ring in this direction, it looks the same initially, but then the next layer out is different. Right here, clearly a CH2 versus here a CH, CH3. So there's a difference there, meaning that this center is now chiral. So what I have to keep in mind about the stereochemistry here is if the OH minus picks off this proton and forms this enolate, when the enolate forms, this negative charge is in a p orbital, so it can overlap with the p orbitals of the pi bond here and be stabilized through resonance. And so that means this carbon is flat. And so the Cl2, it could attack from the top part of that, and the chlorine could come in from the top, pushing this behind. Or, since there's equal electron density on both sides, it could be the bottom part that picks up the chlorine. And so the chlorine could add from the bottom. So I would get a racemic mixture. Now this methyl group, since it's pointing out at me, it might be blocking the top a little bit. So I could say maybe the collision where the chlorine comes in from the top is going to happen a little less often from when it comes in from the bottom, because the methyl group might be creating some steric hindrance during that transition state, so it wouldn't happen as often. So if I were asking you to predict which is minor and which is major, I might say this is a little bit more minor, but the methyl group is far enough away where it's steric, so probably not going to have much of an issue. So it might be like, a very slightly more of this major product versus the minor one we could probably predict. All right, so that's one reaction where enolates attack, or enols, depending on the reaction conditions, attack an electrophile. Another one is the Aldol reaction. So we got a little glimpse at this already today, but this is a major reaction that we'll want to talk about in more detail. So as we were saying before, the Aldol reaction produces a compound that's both an aldehyde and an alcohol. And so it's an aldol reaction. And so if you're trying to identify whether or not this reaction has occurred, one thing you can look for is there an OH group 2 carbons away from the carbonyl, or beta to the carbonyl? What we're also going to see here in a minute is sometimes if there's another alpha proton still there, that alpha proton might be picked off, and it might push out this OH group. So you might also end up seeing something like this. If you end up seeing a pi bond in conjugation, a CC double bond in conjugation with the CO double bond, that also is a possible indication that this reaction went through an aldol and then underwent a subsequent elimination reaction. Right, so if we're looking at setting up syntheses, then these are kind of some of the patterns that give us a clue that an aldol reaction is going to occur. So let's talk about setting that up. So the idea here is we're treating this aldehyde with a relatively weak base. So hydroxide is a strong base. Hydroxide, alkoxide, it's like ethoxide, terbutoxide. Those are strong bases. But compared to the enolate that's going to form, they're comparably or similarly strong, right? So that's going to form an equilibrium, right? We said initially, if we use one of these slightly more weaker bases like OH minus or OR minus, because their conjugate acids have pKa's that are similar to the pKa of the alpha proton, they can pick off the alpha proton and produce an enolate, but not all of the molecules will do that. And the idea is we're taking advantage of that, because if we produce an equilibrium where, you know, somewhere between 5 and 50% of the molecules are in this form, and the remainder percent is in this form, we have a mixture of both. We have the possibility where one could then attack the other. And that's the idea here in the Aldol reaction. Right, so we're forming an equilibrium where some of the molecules remain in this form and some lose a proton from the alpha carbon to produce an enolate. So then the enolate can attack some of the original structure that didn't react, which is what we're showing here. Right, the structure here is the same as this one. So when some of the molecules convert into the enolate, they're then able to attack some of the original substrate that didn't get converted into an enolate. That attack will push electrons up to produce this intermediate here. And then the base can be regenerated because once it picks up a proton and forms either water, or if it was an OR, it would form an alcohol. Then that oxygen can pick up a proton from there and give you the aldol product. And the advantage here is we're doubling the number of carbons in one reaction. That's pretty good. We're going from a 2-carbon reactant, just treating with OH minus, and now we have a 4-carbon product. And we produce 2 new functional groups that give us the ability to do even more reactions. If we want another nucleophile, we could have it come in here and attack the carbonyl. We could make the OH into a leaving group, do an elimination reaction or a different substitution reaction, put something else in there instead. And so this is providing a more complicated, larger carbon backbone with functional groups that we can still further manipulate if we want. So here's another example. Got butanal. 4 carbons would be butane, but if there's an aldehyde on the end, it's butanal. And so we would expect the OH minus to pick off one of these alpha protons, giving the enolate. But it would be an equilibrium since the OH minus is not a super strong base. So only some of the molecules would lose this and be converted into the enolate, and the other molecules would then be able to be attacked by the enolate. So this compound here, call this A, we'll call this B. A is now making a connection between its alpha carbon and the carbonyl of B. And when it does, the carbonyl of B, the electrons swing out onto the oxygen. And there's still 3 more carbons there. That would then usually pick up a proton from water, and you get this product. These reactions are overall reversible, though. So the OH minus could pick this proton back up and go back to the negative. And then those electrons could swing back in and push this out as a leaving group. Normally we don't think of a carbon as a leaving group, but since this carbon can stabilize the negative charge through resonance, it's not a bad leaving group. And so that can also go back. And then this carbon could pick a proton up off of water and go all the way back to the reactant. So this whole thing is in equilibrium. Most of these steps are either proton transfer steps or a nucleophilic attack step, which, especially with an aldehyde, there's not too much steric hindrance to prevent that. So this should reach equilibrium fairly quickly. And when it does, in this particular case, depending on the temperature, we get mostly products, which is good, right? We're trying to make this new carbon-carbon bond here and increase the complexity of our structure. So let's talk about this equilibrium and why it favors the product side. What are some of the factors that cause it to favor the product side? Well, one is we're converting a pi bond into a new sigma bond. Sigma bonds generally more stable than pi bonds due to the electron density sitting between the nuclei more effectively. So that's one reason why the product's favored. We're also producing a nice hydrogen bond here that favors the products. Those are really the only factors that are favoring the products in this case. So converting the pi to the sigma bond is the main thing that drives us forward. So what about other factors? I mean, the OH minus ends up being regenerated in the end. As we said, this last step in the mechanism would regenerate an OH minus when this oxygen gets protonated and becomes an OH. So the OH minus being unstable or comparatively unstable compared to something else, it doesn't matter because it's there in the beginning, it's there in the end. It's acting as a catalyst. So its stability doesn't really affect the equilibrium. So one thing that does affect the equilibrium, though, is entropy. Because in order for this reaction to occur, I need 2 moles of this reactant, and I'm forming 1 mole of product. Right, 1 mole has to form the enolate and then attack the second mole, and so those 2 moles combine into 1, and so that means there's going to be more entropy on the reactant side than the product side. So while the more stable sigma bond is favoring the products, the greater entropy is favoring the reactants. So how can we use temperature to affect the equilibrium? Well, that comes down to the equation for delta G. In this case, we're decreasing the number of moles, going from 2 to 1, so there's going to be less variety and freedom for the structure, less entropy. So there's an entropy decrease, or a negative delta S, and we multiply that by a negative. This term becomes positive. The larger the value I get when I multiply the temperature times delta S, the larger this positive number, the more it's going to make delta G positive, the more it's going to shift the equilibrium back. So really, if I want to favor the products, I want a low temperature. The product should be favored by a lower temperature because increase in the temperature is going to make this positive term more positive or a larger value. And that's going to shift the equilibrium back because it's making delta G more positive. I need enough energy and a high enough temperature to get through the transition state. So kinetically, I need some temperature. But thermodynamically, the lower the temperature, the better, because the more it will favor the product side, which is favored by delta H because the products are more stable with the sigma bond versus the pi bond on the reactant side. So here's another example. Real quick comparison. Here I have an aldehyde as my reactant. Here I have a ketone as my reactant. So it's the same general process. The base would pick off one of these alpha protons, create an enolate. It would do so in an equilibrium. So that enolate, it would result. Only some of the molecules would be converted into that, and the remaining ones would then be susceptible to having an attack at the carbonyl carbon. So that would give this product, but it wouldn't be protonated yet, so it has to pick up a proton from a water, and then you'd have this aldol product. When I look at the equilibrium here, it's basically the same mechanism we just saw, but in this case, the equilibrium favors the reactant side. So we're still converting the pi into the sigma bond. So we still expect the delta H term to be negative, but the degree to which it's negative is going to be much smaller. And the reason for that is due to sterics. Right? So when I have two R groups, which I do on either side of my carbonyl, and I have a ketone, those R groups, whether it's a ring or whatever they are, they're creating some steric hindrance. So when I jam two of these structures together, kinetically, this step is going to be even slower because of all the sterics that's occurring between all the R groups that are connected here during the collision. But this is a thermodynamic consideration we're making, right? So the kinetics isn't really relevant if we're just interested in which side's favored once it reaches equilibrium. So in the products, there's going to be some sterics, right? There's a couple carbons here that have a lot of things attached, and they're bonded to one another, and these things are going to start creating steric hindrance. So that makes the product less stable, right? So normally, due to the sigma bond being lower in energy, if we're just looking at the enthalpy part of it, the sigma bond will be lower in energy than the pi bond that we're starting with. But because of the sterics in the product, it's not going to be much lower. So we still probably have a negative delta H because there's still a slight decrease in the enthalpy, but not very much. So in this case, the fact that we have a positive for the delta T delta S term means that that positive is greater than the negative, and the equilibrium favors the reactant side instead of the product overall. So we can't really get around that sterics. So that brings us to the second quiz question, which was about the kinetics and thermodynamics of these reactions when they're involving a ketone versus aldehydes. So these are the two reactions we just saw. So let's look at them in a little bit more generic way. So let's say we have an aldehyde. There's an alpha carbon here, and so it's going to be deprotonated. Actually, let me draw that a little differently. I want to show the alpha carbon, otherwise it's going to look weird. So here's my alpha carbons, a couple protons here. Since I have an aldehyde, there's not much sterics. Also, from a kinetic perspective, since the oxygen pulling electrons away, creating a lot of partial positive here through induction and resonance, is creating a large partial positive. The hydrogen can't really donate electrons in to help stabilize that. So that's a lot of positive compared to a ketone, where I'd have a carbon here that could donate electrons through induction and hyperconjugation so that the amount of positive here would be less. So if we're looking at the kinetics, the ketone reactant is going to start a little lower in energy than the aldehyde reactant. If we're looking at kinetics, though, we're only interested in the slow step, right? How do we speed up the slow step? If we can, that'll speed up the whole process. So if we're focused on kinetics, we're looking at the slow step collision. So the slow step is not the formation of the enolate. Either one of these would be fast in its equilibrium through which the enolate is formed. The key step for kinetics, which is a slow step, is the attack of the enolate on the electrophile. So when this attack occurs, we're talking about a lot of partial positive here because the hydrogen can't push electrons in and really help to stabilize that very well versus over here. So if this is the slow step that we're going to see occurring next, we have to presume that the first fast step has already occurred, and we're not really interested in showing that on the reaction coordinate diagram. Right, so we're really interested in how the free energy changes in the slow step. And since this aldehyde is starting a little bit higher in energy versus the ketone because of the large partial positive that's here, we expect the aldehyde to be a little more reactive. It's not going to be as hard for it to get to the transition state if it already starts higher in energy. It should react more often. In addition to that, difference in starting energies before the slow step, you have to also imagine what's happening during the transition state. So during the transition states, this is going to attack. This is the slow step. This carbon has to make a bond to the carbonyl carbon and push those electrons up. So with these hydrogens around not taking up much space, I mean, it's still clearly some sterics here with these R groups, creating some steric repulsion. But it's not going to be too bad. The sterics is not going to be too bad because the hydrogens don't take up much space and create much steric repulsion. So the transition state doesn't look too bad. It looks relatively stable. So that'll be the slow step, but it'll be relatively stable to do that step, or relatively small activation energy. So kinetically it will happen pretty often when the aldehydes are involved. With the ketone, now the attack has to occur, and I've got more R groups around. So instead of a hydrogen here, there'd be an R group. Instead of hydrogen here, there'd be an R group. And now these bigger R groups are going to start creating a lot of steric hindrance. So the transition state when the ketone is my reactant is going to be significantly higher in energy. And there's also steric hindrance in the product. So when I have a ketone reacting, it's slower kinetically because the activation energy barrier is higher and most of the collisions won't have the energy to get over there. Also, the delta G value is positive because even though we're going from a pi bond to a sigma bond in the product that's forming here, the sterics is going to make the products a little bit higher in energy. So the ketone is difficult to get through kinetically and the products are not very favored. Versus the aldehyde, where the activation energy is smaller because there's not so much sterics during the transition state, and there's a larger partial positive on the carbonyl, making it a little less stable to begin with. It doesn't take much energy to get up there, and also because the aldehyde's unstable with that large partial positive compared to the products, which don't have a lot of steric hindrance, that actually gives a slightly negative delta G. I don't have space to draw it in there, but a negative delta G, which makes that product favored, right? So that is the explanation for these last two slides, right? With the aldehyde, it's more product favored because there's less sterics in the products and because the reactant has a large partial positive versus the ketone where there's the reactant's more stable, lower in energy, and the products are higher in energy due to the sterics that form there. So the reactants are favored when that one reaches equilibrium. All right, so let's try to predict the outcome of this reaction. So what we have here is an aldehyde, so it should undergo an Aldol reaction relatively easily. And I have only one alpha proton to remove, so I'd expect the hydroxide to pick that off, form an enolate. Sometimes you'll see me draw one resonance contributor of the enolate. Sometimes you'll see me draw the other, right? So far today, I've mostly been drawing the negative and the lone pair on the carbon. But, I mean, really, this is the major contributor, so you could also show it this way a lot of the time. When that reacts, what we're noticing here is this negative charge on the oxygen is pretty similar to OH minus, similar in stability, means I'll get an equilibrium. So some of this will be converted into enolate, and the rest of it will be available to act as an electrophile. So the enolate will attack the electrophile. So these electrons would swing in, come out from the carbon, attack there, and swing up. So how do I draw this? Well, I can draw this part here. Right, this is going to form a new bond there and push these electrons up. So the electrons are now up here. And this carbon are connecting. It's hard for you to see that, which it usually is. Just number the carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1, 2, 3, 4, 5. So 5 and 8 are connecting. 8 is attacking 5. 8 is connected to 9. It's connected to 6 and 7. And it's connected right here to 10. And these electrons are swinging back down to make a CO double bond for 10. Then I would expect this to pick off a proton from the water, and that would give me the product. What about the stereochemistry? Because I've got 1, 2, 3 chiral centers formed now. So what's happening here is when this OH minus picks up this proton and forms the enolate, I'm forming an sp2 hybridized carbon that's flat. So this carbon has lost all of its stereochemical information, and when it attacks the carbonyl, it can do so from the top of it or from the bottom. So that means the carbon 8, which forms a chiral center, will either be connecting from the bottom or from the top, both equally likely, and forming a racemic mixture there. So one way I can do that is to show these zigzags to show that I'll have both stereochemical outcomes at that carbon. Well, also, this carbon here is a chiral center. So what's happening there on carbon 5 is the pi bonds are connecting, or the enolate is attacking. But this carbonyl carbon is also flat, so the enolate can attack it from its top or its bottom, which will either push the OH or O minus that initially forms and eventually becomes an OH forward or behind. So this will also be a racemic, or both stereochemical outcomes will form in a 50-50 mixture for that chiral center. This carbon here, which is carbon 3, is not undergoing any change, right? So this is the molecule that doesn't have its alpha proton picked off, that acts as an electrophile that has a specific stereochemical positioning of the groups in space. There's no reaction occurring at that carbon. So that one should maintain its stereochemistry if this reaction were the only reaction occurring for it. But you have to keep in mind that removal of this alpha proton to produce a flat carbon is a reversible process. Some molecules that will happen to, and then they will go back, and that will usually go back and forth many times before the slow step occurs, which is the next step. This equilibrium will be established, and in the time it's established before the nucleophilic attack here that produces the intermediate from the slow step, most of these molecules, the vast majority of them, will have undergone this equilibrium already back and forth, and that equilibrium itself racemizes, which I think is a fun word, racemizes this center. Because every time this is picked off to create the enolate, and then the electrons swing back in and it picks a proton back up and goes back, that proton transfer where this flat carbon picks up a proton, it could pick it up from the top or from the bottom. And so I would really get a racemic mixture. So you can't really maintain stereochemical information at an alpha carbon in the presence of acid or base because it will racemize it. So really what that means is I get a racemic mixture or every stereochemical outcome at that chiral center as well. So if I have 3 chiral centers, I really should have 2 to the third, which is 8 stereoisomers formed from this reaction from each combination of solid wedge and dash wedge at each of the 3 chiral centers. As we were saying a little bit earlier, often what will happen is the OH that's formed from the Aldol reaction, right? So we got an OH here. It will often act as a leaving group if there's another alpha proton. So that can't happen here because I've got a methyl and an ethyl here. But if either of these groups were a proton, that could be picked off, electrons could swing in and push that out, and you can make another pi bond there. The advantage of that is entropy, because losing some atoms and forming a second mole of product creates more entropy. The other advantage is the pi bond would be formed in conjugation with the other pi bond, which stabilizes the pi bonds and makes it more stable than a normal pi bond would be. So still a sigma bond that we have currently is more stable than the pi bond, but not by much if the pi bond is stabilized through conjugation. And we know heat will shift in equilibrium toward the side with more entropy, the side with more moles. So we can force this to happen with some heat and some acid or base catalyst. And so there's 2 reactions, 2 mechanisms for that elimination process. It's an equilibrium, which we can especially get to favor products with heat, because heat increases the temperature, and the fact that in this process delta S is a positive, then that term becomes negative, and increase in temperature makes it more negative, making delta G more negative, which helps it shift more toward the product side. And that's based on entropy for the most part, because we're forming more entropy when we break this up into multiple structures. So the mechanism for that can happen either way. If I have a base, it will be a one-step E2 elimination. The OH minus will pick off the alpha proton, push electrons in, and push out the leaving group. Not a great leaving group, but it's not any less stable than what we started with. So entropy can take over and make that process more likely to occur. And the OH minus is regenerated, so it's really a catalyst. So ultimately I'm converting this one structure into 2 products, which really helps to stabilize or helps to increase the entropy. If I have an acid, it's going to be a 2-step process. This is going to pick up a proton, making a good leaving group. That'll leave. Actually, it's a 3-step process. Create a carbocation. Then it would be this proton that would be removed, not this one. So water, which would be the solvent with the H3O plus. If the water were to pick off this proton and swing electrons in, the pi bond wouldn't be conjugated with the other pi bonds. It's not going to be nearly as stable. So you can pretty much always expect the new pi bond to form at the site where it'd be conjugated. So on net, I get the same set of products. And so the equilibrium is going to favor those products with heat, because entropy favors the side with more, the equilibrium favors the side with more entropy, the higher the temperature is. When that occurs, you should also get the trans alkene much more often than the cis, also due to the steric hindrance that occurs between groups that are on the same side of the double bond in the cis. Now, sometimes that elimination process we were just talking about is unstoppable. And that usually occurs when you get long-range conjugation, right? So what we just saw over here was we're forming one pi bond through this elimination process, and that pi bond's conjugated with the CO double bond. That helps to make it form more readily, but it's just two pi bonds in conjugation, so it's not, I mean, we need heat to drive this forward to take advantage of the entropy increase. Here, though, you really don't even need heat, and you really can't stop this from occurring because of the extended conjugation that occurs. So if this structure forms, if I use OH minus to convert this into an enolate, and only some of the molecules get converted into enolates, and the rest act as electrophiles for this to attack, push electrons up, and then that gets protonated, you would get this product. So this is the aldol product you would expect, right? It's got the aldol feature, the alcohol, the carbonyl, and they're a couple carbons away from one another. The issue is all these pi bonds here are conjugated. Over here I've got some conjugation, over here I've got some conjugation, but I've got two sp3 hybridized carbons in between separating that conjugation. So if a pi bond could be formed here, which is what we have right here, now everything's in conjugation. So now the molecular orbital for these pi bonds can extend over both rings, the CO double bond, the CC double bond, and that creates a big massive molecular orbital to stabilize all those electrons much more effectively. So not only is there an entropy increase when a proton and an OH produce water because there's more moles of products after the elimination, it also is going to be really a very stable pi bond compared to normal pi bonds because it stabilizes all these pi electrons, giving them extra stabilization due to extra long range conjugation that's forming as a result. So there's no way to stop it. You need a base to make this reaction work, right? We need the base to pick off the alpha proton to even do the reaction. Once that occurs, during that mechanism, the base is regenerated, so it's still there. And you can't stop it from picking off a proton and pushing out an OH and making that other pi bond. So this compound would not even be isolated. You can't stop the reaction. You can't stop the OH minus from coming in and making the other pi bond. So if I asked you to predict the product for that reaction, this should be water. The major product would be this compound, and water would be a byproduct. So we were saying earlier how if we try to do an aldol reaction with this ketone, because of sterics and because of the ketone not having a very large partial positive here, even though the NaOH could pick off an alpha proton from some of the molecules and convert them into the enolate, and that could attack here, the sterics during the attack, the small partial positive, means this process is not very kinetically favored, and the sterics that result in the products means it's not very thermodynamically favored. We would have to keep a low temperature to try to get entropy to at least favor the, to prevent entropy from favoring the reactants too much, because there's two of those versus one product. And so, it's hard to get this equilibrium to favor the products when all that's working against us. If you increase the temperature, though, you can get that product to form, even though the equilibrium favors the reactant side. If a small amount of it does form, which clearly is the case, the higher temperature would allow the elimination to occur that will produce water and this product here. So by removing that and creating a couple sp2 hybridized carbons that are flat, that alleviates a lot of the sterics. Not all of it. There's still clearly, some protons here and protons here that are going to get a little close together and create some sterics. But that process of elimination definitely increases the entropy, because now I've got 2 moles of substance again. And so that actually can be done in a decent yield. So even though ketones don't undergo the Aldol reaction to give you a product favored equilibrium. If you increase the temperature and force the resulting aldol product to undergo elimination, which now increases the entropy, and so that should be favored at higher temperatures, or at least not disfavored, because I have 2 moles of initial reactants and 2 moles of final products. That allows that reaction to be much more product favored. All right, so let's see if we can predict what's going to happen here. We're using some heat, and so that tells me that the elimination is going to occur. You might see heat written out like that. You might see it written out as just a little delta indicating that there's heat going to be added. So the point of the heat is to tell you that the elimination is going to occur after the aldol. So first, there's an alpha proton here. The OH is going to pick that up. That's going to produce the enolate. Again, it's not a super strong base. It's not going to force all of the molecules to produce an enolate, only some of them. Some will remain. I'm going to flip that one over like a pancake so its reactive side is closer to the structure that's going to be attacking it. Oops, should be a 5-membered ring. Fix that up. So this is going to swing in and it's going to attack from here to the carbonyl, pushing those electrons up there. So well, maybe we'll just number these carbons, keep them straight for you. So we got 16 total carbons. So 1, 2, 3, 4, 5. 5 is connected to 6. 6 is attacking 9. So 6 is still connected to 7. 6 is still connected to 8. And these electrons swing back down to form a CO double bond at carbon 8. But 6 is attacking 9. And when it does so, electrons swing out to the oxygen on 9. 9 is bonded to 10, which is bonded to 11. And then the other ring, 12, 13, 14, 15, 16. So then this oxygen, I'm not going to draw it all out because it would take too long, but this oxygen would pick up a proton from the water, that's the solvent there, to make an OH. And then the point of the heat is to help you recognize that it's going to be driven by entropy to break up into multiple moles that have more entropy than this one large structure has due to its limited variety. So this oxygen with its negative is going to attack specifically. I didn't really think about that. What am I noticing here is that normally it would be a proton on carbon 6 that the OH would pick up. And that's because if there were a proton here, the oxygen could pick that up, electrons could swing in and push out this oxygen, and that would form a double bond there that would be in conjugation with the other double bond. So I don't really expect the alkene to form unless it's conjugated with the pre-existing alkene on the CO double bond. And if there's no proton here, which there isn't on 6, there's no proton here, the proton is picked off initially to make the enolate. So there's no proton on 6 to pick off. That elimination is not going to occur, right? So I look for it. When I see the heat, I look for it occurring. But when I notice that there's no proton at that carbon, I know that I can't do the elimination because I can't make a pi bond there without losing a carbon group of some sort, which would occur through a much higher energy transition state and isn't a realistic possibility. So basically that's the product. That's the product I expect there to observe. All right, so far we've looked only at examples where the Aldol reaction occurs between an enolate that forms and an electrophile of the same molecule that the enolate formed from. There's also something called a crossed or mixed Aldol reaction. And this reaction occurs when I have one structure form an enolate and then a different molecule will be attacked by that enolate. And so there are some limitations here. And how do I set up a crossed Aldol reaction? So if I don't take any, if I don't take any strategic precautions, and I just dump in a couple different aldehydes and a base, what's going to happen is the base is going to start picking off protons from either one. So if it picks off a proton here, and these electrons stay behind, that one would be converted into an enolate. If it picks off this proton, that one would be converted into an enolate. And those are different enolates because there's different carbons there. So if the enolate of this one forms, what can it do? Well, if everything's just dumped in together, it could attack here on a molecule of this that didn't form an enolate, or it could attack here on a molecule of this that didn't form an enolate. So if this structure, attacks the other red one, I would get red plus red, and that would eventually produce this product, where this carbon would be connected to that carbonyl, pushing electrons up, which would eventually become an OH, and I still have one more carbon there. I could also have the red attack the blue. If the red attacks the blue, this carbon would connect to that one, push electrons up, which would eventually become an OH, and now there'd be an ethyl group there instead of a methyl, which is not the exact same product as the other one. So you start to see this going to become a mess. If the blue forms an enolate, and when I use a relatively weak base, both of these would form some enolate and some not, the result of the blue enolate could attack either one of those. And so if the blue attacks the blue, then that attack would produce this product, which is also a little different because there's ethyl group here. It's attacking the other one, and that one has an ethyl group. If the blue attacks the red, I would get another slightly different product that would result. So there are 4 technically different products. Each of these is unique in the connections and structure that form. So if I get this complex mixture of products, this is not practical. I don't want to run the reaction like this. So there are ways to get one aldehyde to form an enolate and attack the other in a controlled way that only produces one product. And that's what we're going to talk about here for the last bit of the lecture. So one strategy to do this kind of crossed Aldol reaction is if one of your compounds cannot form an enolate. It doesn't have any alpha carbons. So it doesn't have any alpha protons. It can't form an enolate. So in this case, I don't have to worry about multiple types of collisions and different enolates attacking different electrophiles and forming different products. The only thing that can happen is the OH minus could pick off this proton, form that into an enolate, have it attack, push electrons up, and then protonate that. And so that gives me one possible product. And so that should give me a good yield. And so that's a practical reaction I can do. Right? So that's one strategy. If one of your reactants can't form an enolate, only the other one can. You can rely on that one forming an enolate and doing the attacking and then predict the product that would result. Another example of that here, there's no alpha proton. So I don't have to have a situation where there's no alpha carbon at all. As long as I have an alpha carbon that doesn't have a proton, I still can't form an enolate there. So the only option again is to have the other compound form the enolate and attack and eventually pronate that. In this case, though, I would expect the uncontrolled elimination, even without the heat. So the heat's kind of a giveaway there that the elimination is going to occur, but even without it, I would still expect this proton here to be picked off, pushing electrons in and pushing out that leaving group, because that forms a pi bond that's conjugated with the pi bonds of the ring as well as the CO double bond, and also producing the water in the process of that leaving really is an advantage from an entropy standpoint. And so that's the product that I would predict after these two react. But the key thing is I'm getting like one major product. So this is a practical reaction that I can do specifically because only one of my reactants can actually form an enolate. So here was the quiz, the last quiz question of the day. Just to point out, I was going to say more strategies here. We've only had a chance to see one strategy, and we've seen two examples of it. There are more strategies, but we're going to get to those next time. Obviously, we're running out of time here. So to discuss, we'll pick up with that on Monday. But in relation to that, the last quiz question that was due today, just a look at the reaction from a retrosynthetic perspective, right? So if I tell you, I want you to make this product from an aldol reaction, you have to think about how to disconnect, right? So the way you would do that, if you're thinking it's going to be forming from an aldol reaction, is you would find the carbonyl carbon and the OH carbon. And you would disconnect right here, retrosynthetically. This is the sigma bond that's going to form in the forward direction, so retrosynthetically we have to break that bond. How do I know that? Because it's always the alpha carbon, the carbon that's one away from the carbonyl, that attacks what used to be a carbonyl, pushing electrons up to become an OH group. So this is the nucleophile. This carbon here, it's got a methyl and an isopropyl. And that carbon is going to be the enolate. It's going to attack this other group. And I'm going to set this carbon here up as a carbonyl carbon. So maybe it'll helpful if I number these 1, 2, 3, 4, 5, 6, 7, 8. And then the ring I'm not going to number because that's pretty easy to keep track of. So I've got 1, 2, 3, 4, 5, 6, 7, 8, right? So carbon 3 has a lone pair. It's going to attack carbon 8. That makes the connection between 3 and 8. So I'm always going to disconnect between the alpha carbon of one compound and the OH carbon of the other, because I know in the forward direction this is going to attack here and push electrons up, and that oxygen is going to be protonated and become an OH. In order to make the enolate, I would obviously have to start with that and add like NaOH or some other base to pick off this proton and put the lone pair on there. But this should work because only one of my reactants actually has an alpha proton. And the OH should pick off this one and not any of the ones over here, because when it picks off this proton and the electrons stay here, they're gonna swing in and form an enolate that's substituted with carbons. So the pi bond here that's going to form when this swings in and pushes up the other resonance contributors, more stable because of the carbon-carbon pi bond being substituted with carbon groups. So I expect that reaction to occur as advertised in the forward direction. However, and I excluded the next part to make the quiz question easier, but this is not really the product that you would expect. Actually, no, it is. I take that back. I won't carry it away. If there were still a proton on carbon 3, I would expect OH minus to pick that off, swing electrons in, and push out this OH minus to make a pi bond here. Because that would connect the conjugation of the ring with the conjugation of the CO double bond to make an extended conjugation system. So I'm looking for that always. And I can see how that extended pi system would stabilize the structure, but since there's no proton to pick off, I obviously can't make a pi bond between 3 and 8, so that would be the final product there. So here's method 2. Okay, we're going to talk a lot more about this one in detail next time, so this is basically just an intro to it. The idea here is, even though I've got alpha proton that could be picked off from this compound and from this compound, I'm going to do this stepwise. So in step 1, I'm going to take the one that I want to form into an enolate and add a very strong base, the LDA. We talked about this one. We said it's sterically hindered. It's got a full negative on a nitrogen, very unstable compared to a negative that's stabilized between an oxygen, especially in a carbon. So that should react more 100%. If we look at the pKa values we saw earlier, the pKa of the protonated LDA is much higher than the pKa of the carbonyl alpha proton. So this reaction should shift exclusively to the product side. So the idea here is, this is not an equilibrium. I'm converting basically 100% of the aldehyde or ketone that I want to be my enolate into the enolate in one step, and then later in a second step I'm adding the other ketone or aldehyde that I want the enolate to attack. So I form the enolate first with a very strong base that shifts it 100% forward. Then I add the electrophile so that can attack and push electrons up. And then I would add some kind of proton source to protonate that and give me the alcohol or aldol product. So that would be step 3. I can't have water around the LDA because LDA is very unstable, a very strong base. It would just pick a proton off of water and convert the water into OH minus. OH minus is not strong enough to shift this equilibrium 100% forward. So if I were to use this substance here with NaOH, since it would form an equilibrium enolate, and that would be an equilibrium, only some of that compound would be converted into enolate and it would start attacking other molecules of the same compound. That's not what I want. I specifically want this enolate to attack this compound because this is a product I'm trying to make for some reason. So I need a strong base. I can't use water. That base will react with water to make a weaker base. I need the LDA specifically because it's strong enough to pick off every proton, convert this 100% into the enolate in one step, and then later I add the compound I want the enolate to attack once I believe that has occurred. Then that attack can produce this intermediate with a negative on the oxygen, and then a proton source would protonate that, and I would get this product. And so one more, there's a couple more slides here. I thought that was pretty much it. One other example here, we got a situation where we want to make this product. So if you see a pi bond in conjugation with a CO double bond, that suggests that if you had worked backwards, what you needed before that would have been an OH here. because whatever base is used to do this process, the OH could be picked off, or the proton could be picked off and push that out to make the pi bond there. So working backwards further, I can come up with, an Aldol reaction. So if I start with this reactant, this carbon here can be made into a enolate, and it can attack this carbon here. This is tricky though. I have to do this in a controlled way. So for the synthesis here, I want to get these compounds to connect. I want to convert this one into enolate and have it attack the other one. All right, so I'm just kind of like working things through in my mind here. How do I make this enolate and not have my base pick off a proton from here and make this into an enolate and have it attack the other one? And so I have to do this in a controlled way. So I ran out of space. So what I'm going to do here is I'm going to start with the one I want to be the enolate, which is this grouping here. And the first thing I'm going to do is add LDA. The LDA, which the L is for the lithium, it's just a counterion, it doesn't do anything. Diisopropyl amide is a very strong base. It's going to pick off a proton from here. Why won't it pick off this proton? Because there's too much steric hindrance, and that's why these groups are on here. These large bulky groups make it hard for it to pick off protons from sterically hindered sites. So with the LDA, the point of it is that it's strong enough to convert all of this into an enolate, but it's also sterically hindered, so I can predict that the enolate will occur on the less sterically hindered alpha side. So that'll give me this enolate. That's going to be the result of the first step. The second step, I'm going to add the extra carbons. So I want 3 more carbons, and I want it to be an aldehyde. So that will attack, shows electrons up. That will give me this intermediate. So before we had water around, this could pick up proton. We don't have water. We can't use water with the LDA. There's no point in adding it here. We don't want this enolate picking off a proton from water. We want it to attack this carbonyl, so we would just add the carbonyl. So then a third step, that's where I would add H3O plus and heat. And the H3O plus would be dissolved in water. And so in terms of how that would work, this oxygen would obviously pick up a proton from the H3O plus once. And as long as I have excess of that, it would pick up another proton from the H3O plus and make a great leaving group. Then it could leave, create a secondary carbocation, which is reasonably stable. Oops. There. And then the water would pick off this proton, push those electrons in, and make the pi bond. And the heat is there to help drive this forward by entropy because it produces a water byproduct, and extra moles of products helps, is going to be more likely to have higher entropy, and the heat shifts the equilibrium toward the side with more entropy. And so there's a lot of practice you can do around those reactions. And just so you know, one other quick point. These aldol reactions can occur intramolecularly as well. So if you have 2 different electrophilic sites and you add some base, I wouldn't expect this proton to be picked off. I mean, if it were, then I wouldn't get the cyclic or intramolecular reaction, because the negative charge here is only a couple atoms away from this carbonyl. It wouldn't be able to attack. The angles wouldn't allow for that. So if the outside proton were picked off by an OH minus, that would form this enolate. And that's 1, 2, 3, 4, 5 atoms away. 1, 2, 3, 4, 5 atoms away from an electrophilic site, so it can attack intramolecularly, which would initially produce this compound. Right, the electrons here would attack there, push these electrons out, and then eventually that would pick up a proton, become an OH group. And then if the heat tells me I want to look for the subsequent elimination reaction, so the heat would then pick off this proton. Now the heat wouldn't, but the heat would drive this equilibrium toward the product side. The OH minus that's regenerated would pick off this proton, swing electrons in, and push that out. And that would give me the pi bond there. So you want to be aware of 5 and 6 membered rings forming through this Aldol reaction as well. As long as you can make an enolate site that's 5 or 6 atoms away from another carbonyl, that would you would expect that to happen intramolecularly. Because the 5 and 6 membered rings have very little ring strain, very little angle strain or torsional strain associated with 5 and 6 membered rings. All right, well, that's a lot. So enjoy practicing that. And we will continue discussing Aldol reactions and modifications of Aldol reactions on Monday as we continue through chapter 22. But please do let me know anytime in the meantime if you have any questions about any of the practice you're doing or really anything else. So here is the